So in this video we're going to look at the definition and use of inverse trigonometric functions based on right triangle definition of trigonometric functions. And what we want to do first is just remember what an inverse function is, practically speaking. So if we have a function f, so if we have a function f of x, where y equals f of x. This is a function where we input x and the output is y. So the inverse function, if it exists, the inverse function f inverse is a function that inputs the y value and outputs the x value. So the inputs become outputs and the outputs become inputs. So we get a function x equals f inverse of the inputs are the y values. In other words, with an inverse function we have inputs, with a regular function we have inputs, and then we have outputs. Regular function wasn't a good way to say that. We have inputs and outputs. The inverse function takes those outputs and uses them as its inputs, and then takes the inputs for the function f of x and uses those for its outputs. So in the context of right triangle definitions for trigonometric functions, we've defined 6 functions so far. And for example, we have defined the cosine of theta. So the input is the angle theta. So we input an angle, and the output is a side ratio, and the specific side ratio that it is the adjacent over the hypotenuse. So we input theta and the output is adjacent over hypotenuse. So if there is an inverse function, then the inputs need to be the side ratio, the adjacent over the hypotenuse, and the output needs to be the angle that generated that side ratio. So the inverse functions, we give them names. So the cosine of theta has an inverse function called the arc cosine, and we know the input into the arc cosine is a side ratio. It's a specific side ratio, the adjacent over the hypotenuse, and the output is the angle that generated that side ratio. We can also name the inverse function cosine inverse. So arc cosine and cosine inverse are synonyms, but we still get an output of theta based on an input of the appropriate side ratio adjacent over hypotenuse. And then if we think about function composition, we can say, hey, what if I start with the cosine function and I input into it the inverse function cosine inverse? Well, what do you put into the cosine inverse function? You put side ratios into it, adjacent over hypotenuse, the specific side ratio. The cosine inverse generates an output, theta, and then the cosine of that theta generates the side ratio as the output. So the cosine function generates the side ratio as its output. Or we can think of this as the cosine and cosine inverse cancel each other, giving us the side ratio. I kind of don't like to think about it that way, but that would be another way to think about it. We could also look at doing the function composition in the other direction. So we could say, hey, what if we took the inverse function, let's use the arc cosine name for the inverse function this time, and we input into it the cosine function. Well, here's the cosine function, and he requires that he be given an angle as the input. He's going to generate a side ratio. That side ratio goes into the arc cosine function, and the arc cosine function spits out the angle theta. So you can think about them as canceling, or you can just recognize the fact that the arc cosine of a side ratio is going to generate the angle theta. So the other trig function that we looked at was the sine of theta, or one of the other functions we looked at, sine theta, and it was defined to be the side opposite theta divided by the hypotenuse of the right triangle. So the inputs are angles and the outputs are the side ratio generated by that angle. So if we have an inverse function, the inputs need to be the appropriate side ratio, opposite over hypotenuse, and the output will be the angle that generated that side ratio. Again, we're going to call it the arc sine is the name that we're going to give the inverse function. It's going to be the arc sine of the appropriate side ratio. You feed it opposite over hypotenuse. You can never put an angle into the inverse trig function because the inverse functions are expecting side ratios as their inputs, and when you put an appropriate side ratio in, it pops out the angle that generated that side ratio. And again, just like with cosine, we can also use the inverse function notation, sine inverse, but again the input will be the appropriate side ratio, the one that goes with the definition of the sine function, and the output will be the angle that generated that side ratio. And if we're doing function composition, if we feed the inverse function arc sine into the sine function, so there's going to be a side ratio inside of that arc sine function, and the sine function is going to generate as its output the side ratio. Side ratio. And if we do the composition the other way, if we do the arc sine of the sine has to have an angle inside of it. We feed the sine function angles, and the arc sine is going to output an angle for us. So the same game we could play one more time. We could play it with the tangent function. We could say, hey, suppose I want the tangent of theta. Well, this function generates a specific side ratio. Tangent of theta was defined to be opposite side divided by length of adjacent side. So the inputs are the angle and the outputs are the ratios of opposite lengths to adjacent lengths. So if we have an inverse function, the inputs to the inverse will be the appropriate side ratio, opposite over adjacent, and the output will be the angle that had generated that side ratio. So again, we're going to name the inverse function the arctan, and the input is going to be the appropriate side ratio, and the output will be the angle. And we can also use the classic inverse function notation, tangent inverse, but we're still feeding it the correct side ratio, and it's giving us the angle that generated that side ratio. And function composition is going to work like you expect it to. The tangent of the inverse tangent of its appropriate side ratio. The tangent, when you plug something into the tangent function, it outputs the side ratio. And if we do the composition in the other direction, so we feed the tangent of theta into the tangent inverse. When we're feeding something into the inverse tangent function, it's going to output the angle for us. Now on the calculator, these inverse functions, cosine inverse, sine inverse, tangent inverse, all are on the keys corresponding to the sine, the cosine, and the tangent. So the sine inverse is directly above the sine. You have to go second sine to get to the inverse function notation, or second cosine to get to the cosine inverse notation, or second tangent to get to the inverse tangent notation. So only on the calculator, on your graphing calculator, usually only the sine inverse, cosine inverse, and tangent inverse have keys that go with them. So the problem then is that we defined three other trigonometric functions that don't have keys on the graphing calculator. So we defined the secant of theta. The secant of theta was the reciprocal of the cosine function, so it was the hypotenuse over the side adjacent. We defined the tangent function, the cotangent function. Cotangent function, feed it an angle. It gives you the reciprocal of the tangent function, so instead of opposite over adjacent, it is adjacent over opposite. And we defined the cosecant function, which was the reciprocal of the sine function, so it's just the hypotenuse over the side opposite of theta. And so we can run into an issue where we need to know the angle, that is generating this ratio. And if that happens to you, you just want to remember that the secant of theta is the reciprocal of the cosine function. So just convert it into a cosine world. Hey, the cosine of theta is the adjacent over the hypotenuse. And then you can use your calculator to work with this. So we just want to recognize that, yes, each of these do have inverse functions. The secant, the inverse function for the secant is the arc secant, and you feed it the hypotenuse over adjacent, or you can use the classic inverse notation, inverse function notation. You'll be feeding it this. It does give you the angle, but the calculator doesn't have keys for these. And if we need to get at something like this, we're just going to convert into a cosine, sine, or tangent world by using the fact that secant, cotangent, and cosecant are reciprocals of cosine, tangent, and sine. So they still have inverse functions. So the cotangent, its inverse function is the arc cotangent, or the cotangent inverse, and you would be feeding it the side ratio, and it would output the angle. You would feed it the appropriate side ratio, it outputs the angle, and this would be the arc cosecant. Feed it the side ratio, it outputs the angle, or use the classic inverse notation. Feed it the side ratio, it outputs the angle. But again, no keys on the calculator for these, so we have to convert them into cosine, tangent, or sine world. So first example, very simple. Use the calculator to approximate the acute angle whose corresponding ratio is given. And so we need to decide, do we want theta in degrees, or do we want theta in radians? What measure do we want for our angle, degrees or radians? So let's decide that we want to get the angle in degrees. So we're going to go cosine of theta. I'm going to rewrite the problem. And then I'm going to use the inverse function. I'm going to apply the inverse function to both sides. So I'm going to make both sides of the equation the input into the inverse function, the cosine inverse. So we'll take the cosine inverse of both sides. The cosine inverse is a function, so the stuff should be going into the function. Don't do things like write cosine inverse like this. That will always get you marked down. Cosine inverse, the output to the cosine inverse function is always the angle, so the angle pops out, and we have the cosine inverse of this side ratio, and this is the exact answer. And if we're supposed to approximate it, now is when we grab our calculator. So we're going to keep that, pull the calculator up, and we want the cosine inverse of 0.3090. I want the answer in degrees. So I check my mode. I make sure that I'm in degree mode. I'm already in degree mode, so I'm in good shape. So I'm going to do the cosine inverse. So second cosine, and then input the side ratio, which is 0.309. Close that parentheses off and hit enter. And we get about 72 degrees. So it is approximately 72 degrees, and because I rounded, I'm using the approximately symbol. If I'm asked for, if I want to know the angle that generated the side ratio 1.5, that means I need to solve for theta to find the angle. It says find the acute angle. It's an acute angle because we're doing right angle trigonometry, which means we have two acute angles on that right triangle. So the secant of theta equals 1.5. We could use the inverse secant function. So I could go the secant inverse of the secant of theta equals, I made the left hand side an input into the secant inverse function, so I make the right hand side an input into the secant inverse function, and I get theta equals the secant inverse of 1.5, and this answer is exact. If I want to approximate it, the issue is that there is no secant inverse key on the calculator. So if I want to know theta approximately, what I want to do is take my secant of theta equals 1.5 and recognize that the secant is the reciprocal of the cosine. So maybe even an easier way to do this is to recognize that 1.5 is the same as 1.5, is the same as 3/2. So if the secant is the reciprocal of the cosine, that tells me that the cosine of theta is equal to 2/3. And now I can use the cosine inverse of both sides. So let's use the arc cosine form. Arc cosine of the cosine of theta equals the arc cosine of 2/3. The arc cosine function will output the angle theta. So theta will equal the arc cosine of 2/3. And if I want to approximate it, now I go to the calculator. Again, if I need to decide whether I want the angle in degrees or radians, let's do it in radians this time. Get the angle measure in radians. So the arc cosine of 2/3, or the cosine inverse of 2/3. Let's take our calculator and use the second cosine inverse key and put 2/3 in there. And we get about, whoops, that's degrees, 48 degrees. I said I wanted the answer in radians, so I have to go into mode. I'm in degree mode. If I want the answer in radians, I need to switch over to radian mode first. Again, this is the easiest mistake to make, is to not put it in the correct mode, and then go second cosine to get at the cosine inverse function. Cosine inverse of 2/3, enter, and it's about 0.84 radians. So about 0.84 rad. So another example. So it says select an appropriate function to find the indicated angle. So each of these has an indicated angle, meaning that it's labeled. And then it says round to the 1/10 of a degree and a 1/10 of a radian. The angle measure, let's do this one in degrees. Let's find this one in degrees. Let's do one in degrees. Let's do one in radians. And the key here is they've given us two sides. So we need to think about the relationship between these sides and this angle. And I want to recognize that 6 is the side opposite, and 18 is the side adjacent the angle. And then that leads naturally into using the tangent function, because the tangent of an angle by definition is opposite, which is 6 over adjacent with it, which is 18. And this will be the tangent of theta simplifies to 6 over 18 is the same as 1/3. And now to get theta by itself, we take the inverse tangent of both sides. So theta is the tangent inverse of 1/3, and then if we're approximating it in degrees to 1/10, to a tenth, the nearest tenth, I'm going to go theta is approximately equal to, and then we're going to go to the calculator. We're using the inverse tangent function, so I'm going to go second tan to get at the inverse tangent function. We're inputting the side ratio 1 divided by 3 into that function. We'll check our mode. We're in radians. We wanted that angle in degrees, so we need to switch over to degree mode. Then I'll go second quit and go ahead and hit enter. And we have about 18.4 degrees. So this is approximately 18.4 degrees. On this triangle, we're going to find beta in radians. And we have two sides, and what I want to recognize is that this side is opposite beta. And this side length is the hypotenuse. So I have opposite and hypotenuse. That's going to lend itself naturally to the sine function, because the sine of an angle beta is going to equal the side opposite beta divided by the hypotenuse. And then I take the arc sine of both sides. The arc sine or inverse sine of 14/5. Arc sine cancels the sine, giving us the angle, or the output to the arc sine function is always an angle beta. Arc sine of 14/15. This is exact. And then if we want to approximate it to the nearest tenth, we go to the calculator. We'll keep that. We go to the calculator. We're using the inverse sine function, so it's going to be second inverse sine of 14 divided by 15. There's the side ratio being fed into the inverse trig function, and then we need to go into mode, and to get an answer in radians we need to select radian mode, second quit to get back out to the main screen, and then we hit enter, and we get about 1.2 radians to the nearest tenth. So mark that down. This is 1.2 radians.